Okay, let's take a look. Okay, so you're already read the passage. You'll see that there's a few points based on temporary hardness and permanent hardness. And then the question wants us to show how the data works, which is this thing here, support display. So let's look back a little what are all these hardness. So what we can see here is anything that's temporary hardness is due to thermally unstable compounds like this. Permanent hardness is due to sulfates, hydrocarbonates, or chlorides. So fundamentally, this is the classification. So softening means removal. So we can see temporary hardness can be removed by boiling. Permanent cannot be removed by boiling. So if you want to soften this permanent, the ions, the metal ions that causes this hardness must be removed. So the case here is to add sodium carbonate to PPT out these ions. So essentially, that's the fundamental difference. So there's this soap test that is required because over here, the question says soap solution. So I look at the soap test, it says hot water doesn't lather easily. Okay, if you don't know what's lather, simply it's just formation or bubbling. So hot water together with soap don't bubble so easily. And then soft water, they form bubbles very easily. So less soap for the same cleaning effect. Okay, so that's all for that round. Patrick, the sound not stable, is it? The rest of it, you got problem listening? Am I breaking out at different points?
It's very muffled.
Very muffled. Okay. Yeah, let me change this. All right. So the question here says A contains temporary hardness. So one wants us to conclude yes, temporary hardness. So temporary hardness include things like they lather easily and things like that. So the question says the volume of soap required. So prior to this one, they have hardness. You notice that they require quite a bit of soap before they lather. And it also shows that after the boiling process, A simply require the same amount of soap as normal distilled water. So A must have been temporary because upon the boiling process, it makes it easier for it to lather. So the role of distilled water, right? We can say that it is actually used as a control. And in this case, we say it requires 1.0 cm cube, right, of soap to lather. Oh no, I might lose it. Oh, never mind, only a bit. Yeah, rewrite again. Okay, so comparing against distilled water, we can see that sample A. Okay, at the same time, it also requires 1.0 cm cube of soap to lather. So as a result, we can say that A must have been having a temporary hardness that has been removed by boiling. Remember, the concept is the harder the water, the more soap you need. So at the beginning, when there is some hardness in both sample A and B prior to boiling, both of them require quite a significant amount of soap compared to distilled water. So this shows that there are ions over there that makes the water hard. But after the boiling process, the boiling removes the hardness in A, so that shows temporary hardness. And then for B, we can say that for sample B, it will still require 7.0 cm cube of the soap, right? After boiling. So this suggests that although there's a over here we see a reduction in the soap use. Before and after boiling. So this supports the case where it shows that B contains, right, both temporary and permanent hardness. Okay, so by looking at the soap value. Okay, any questions for this? If not, I go to B. Remember, hardness is just a factor of how much ions is present. So the question in part B says, show how the data above show that sample B contains equal amount of temporary and permanent hardness. So again, if you have to use the data above, the only data we have is through soap volume. Okay, so I can say that total volume total volume of soap needed, right, to lather the temporary and permanent water, or permanent hardness. Okay, the total volume we have here is 13. For distilled water is 1. So by default, right, the water will require 1 cm cube of soap to lather. So with the hardness, temporary and permanent hardness, the total volume was 13. So if we subtract this away, the amount of soap required will be 12 cm cube for both temporary and permanent hardness. If they are both present, the total amount of soap required will be this amount. Okay, so after the boiling process, we say that the temporal hardness is removed. So I'll say that the volume of soap required to remove for the lathering of the temporary hardness because initially we need 13 and then we minus away the final volume here, 7. 7, this is all hardness already. So if I subtract away 7, that means strictly for volume of soap for temporary will be 6 cm cube. Then what about the volume of soap required for the required for permanent hardness. The remaining permanent hardness is 7. You minus away 1 cm cube for the water, because even for water, you also need 1. So you minus off the volume required is this. So this will indicate that the volumes are the same.
Wait, why do you minus 1 to the 13 to find the soap needed for temporary and permanent?
Okay, this portion here is just to show that for both temporary and permanent, the total is 12. Alternatively, right, for this step, right, I can also do 12 minus 6, which is the total volume needed, minus away temporary, I get the permanent. Either or is okay. The 12 actually, to be very frank, like a bit redundant, right, this one. This one might look a bit redundant. So technically speaking, if you just do these 2 steps, right, actually it's also okay. All right, Ken? The front part, I just want to show that prior to boiling, the 12 cm cube is for both of them. Other than that, does it really help to prove? I don't really think so. The one that used to prove the same volume is this. Now, C is the first concept question. How does temporary hardness reduce by boiling? Boiling, I would say, is probably high temperature. So let's take a look at what is temporary hardness. So temporary hardness is either unstable magnesium hydrogen carbonate or calcium hydrogen carbonate, AQ. And the question here says thermally unstable. Thermally unstable indicates that it is very likely to undergo thermal decomposition. And this is thermal decomposition of hydrogen carbonates. So if we have our equation, let's choose the case of magnesium hydrogen carbonate. Hydrogen carbonate have this formula, HCO3 minus. So for magnesium hydrogen carbonate, magnesium with a 2+ charge, we should have this as our final compound. The question says it's dissolved in water, so this will be accorded an AQ state. Okay, so next thing is, remember we said boiling can remove the hardness, right? So that means the minerals are no longer inside. The minerals are no longer in the aqueous solution. And it's always due to, as let's go back again, due to the ions formation, due to the calcium and magnesium ions. So if they do not remove, they will start to build up all this hardness. So if we want to remove, if magnesium can be removed through the heating process, that means you must have formed, right, a magnesium compound that's in a solid state. So that, because the question in front has already mentioned, all these ions are removed by precipitation. Okay, it's the removal of the precipitate of calcium and magnesium ion through the additional of sodium sulfate. But also temporary, once you boil them, they will break down already. So it is the precipitates. Now, based on these statements, because it's sodium carbonate, the precipitate here that's likely to form, right, when you remove the calcium or magnesium ions, is very likely calcium carbonate and magnesium carbonate. Because the magnesium and the calcium are both in the solution, making the water hard. So if you want to soften it, it is just the simple concept of precipitation of the calcium and magnesium ion. And the precipitation here is carried out using sodium carbonate. Okay, for the permanent ones. So for the permanent ones, we precipitate them in the form of carbonate. So when we look at the temporary hardness, is due to this few, but because they are thermally unstable, they will be broken down upon heating. So if you look at the compound here, right, there's nothing else I can form.
There's literally nothing else I can follow. We may not have studied, right? We know magnesium carbonate, when it breaks down, it forms CO2 and magnesium oxide. But what about hydrogen carbonate? Okay, it is a case where we don't really know what is being formed over here. But if you look at it logically, right, what kind of negative ion we can write? There's no other choice. The only thing that I can write here is magnesium carbonate. Okay, because if you look at a negative ion, other than carbonates, I don't have any other choices. So the decomposition of the temporary hardness ion or the temporary hardness compound magnesium hydrogen carbonate upon heating, upon boiling of the water, the 100 degrees Celsius will break down your hydrogen carbonate into magnesium carbonate. So this magnesium carbonate is precipitated out from the solution. So now your water does not have free moving magnesium ion anymore. Previously, it was AQ, now it is solid state. So this is known as the softening effect of boiling. So the magnesium ion are being extracted. Now the other problem is, what are the remaining products? So if you try to do a balanced equation, you notice we only have these two options. Otherwise, we can't really balance the equation. So even though we do not really learn this equation in syllabus, but by getting hints from the passage and getting hints from the formula of the hydrogen carbonate, you notice the only precipitate we can get is your magnesium carbonate. So gas and liquid. Okay, so remove. So this is removed as a solid. Okay, any questions for this? Of course, you can choose calcium, then everything will be the same, except that magnesium replaced by calcium. The equation is exactly the same. All right, any question for me? Please not give you a minute to jot down whatever you need, and then we move forward to the next part.
So for part C, just need to write the equation.
Yeah, it says using equation, explain how the hardness can remove by boiling. Yeah, okay, actually, if you want to, we can talk a bit more. So we can say that, oh yeah, the explain part. Okay, let me put this down. Okay, so we can see something like this. Okay, because it's insoluble, we can remove it by filtration. Okay, so removal of ions from aqueous solution is also AKA known as PPT reaction. Just to confirm, other than Kyoko, any one of you, your school have started on organic chem? Nobody, right? Okay. Oh, Frederick started on alkanes. You said you're on propane now, that means have you drawn isomers yet? Have you done isomerism? Okay. And next week we are starting with. Okay, another method to remove permanent and temporary hardness. This because the temporary or permanent hardness is due to aqueous ions, right? So if you want to leave the ions behind, we just want to extract the pure distilled water. This is a salt solution. So salt solution, if you want the pure solution, the easiest way is to do simple distillation. So when we do simple distillation, the pure water will distill over, the salts and all will be left behind. So instead of going through the process of all the precipitation process and filtering process, you can just simply do simple distillation to boil off your solvents. Okay, that's all. Part E, disadvantage, hardness disadvantage because it causes a buildup of limestone. Okay, this limestone, right? So because of the calcium presence, in fact, this thing here is very prominent now. I'm not sure if you guys have seen before. This is this kind of formation is very common in your if you use those electrical steamers, or you use those hot pots, right, to boil water, those temporary boiling of water, right? Using those electrical pots, over time, right, you will start to see white powder forming on your steamers, white powder forming on your this all this electrical kettle. Okay, and it's due to the same reason, because of all these ions present in our tap water. So especially for electrical steamers, the water being boiled off. So the steaming process is pseudo simple distillation. So over time, when you boil it, when you use your steamer, especially when you steam until the water reservoir, right, in your steamer has dried up, you will see that the remnants right behind. Sometimes over time you will see all these scales or so-called limestone. We call it lime scale, but they are basically carbonate accumulated on your steamer. And sometimes you'll see all these scales appearing in your kettle. So those are some of those home hacks where they suggest how to remove all this powder, right? Is to use white vinegar or use things like lemon juice solution. Okay, this is the concept of neutralization again, where you use, because vinegar is organic acid. Okay, when we do organic chem, you'll see vinegar falls under a few categories. Most of the time, vinegar has the formula of is also commonly present in or rather vinegar commonly has ethanoic acid. So being an acid, it can help you to descale. So what does descaling means is removing all the white calcium carbonate that's left behind after your steaming process or after your kettle, you use your kettle to boil some water. So all these things that's left behind is due to the fact of hardness present in our tap water. So over here, the question says, right, because of this hardness, sometimes you have all these things left behind on your pipe, like the same way the powder is left behind on our steamer, on our kettle. Okay, but it says that over here, most of the time it's a disadvantage because all this can cause clogged up, especially in water pipe. This buildup might cause water flow issue. So you might have a pressure, when your water is water flow is being disturbed, you might have pressure issues for your household, and sometimes it might cause clogged up. But over here, it mentions that despite all these disadvantages, there could be advantages of this lime scale in the water pipe. Remember, they are calcium carbonates, right? So they are essentially just an insoluble salt. So one of the advantage, right, when you have all this powder forming in your pipe, right, is that because calcium carbonate, if you look at the properties, It is an ionic compound, so the melting boiling point tends to be high. And it's also insoluble. So it kind of makes this a very, very hardy material. So because of this hardy material form, right, it actually can help to do something to your water pipe, especially if it's a still water pipe. Okay, it's something like a coating. Okay, all these lime scale, they can technically form a coating. And let me be a bit more obvious. It can actually form a protective coating on the surface of the water pipes. Hugo, why do you think this coating is an advantage, even though it might have issue of clogging up and everything? What can it actually help you? And because I use the word protective coating, what is it protecting?
The pipe.
What does it protect it against?
Huh?
What does the coating protect it against?
Rusting.
Yeah, correct. It prevents the water pipes, right? Rather, it protects the water pipe from rusting. Okay, it's the same way as paint and all the physical methods. So it prevents the water pipe from rusting by forming a barrier between the pipes and the water, and a barrier between the pipe and oxygen gas in the air. Because it has these kind of properties. Technically, all this skill build-up is not good. So this E here is just I would say it's a theoretical, just a theoretical question. In real life, we will always want to remove away all those skills. Okay, so part E says you have crops, and then it says that the crop says it has a slightly acidic soil. So what happens is that if you want to, you spray water into it, right? So this slightly acidic soil plus water, it will give the water an acidic pH. So this acidic soil will make your so-called water acidic. And if you want to reduce the hardness of this acidic water, it becomes an issue. Okay, as we can see, it's the carbonate thing. So remember, what's the role of carbonates? To remove hardness, we want to form a precipitate. We want to PPT out the calcium or the magnesium. But if your carbonate get reacted, then there's nothing to PPT, right? So the effectiveness will actually be so-called affected. Okay, so what I will say here is, so if we were to do this, if our purpose is to throw in the sodium carbonate, right, to remove the calcium, to remove the magnesium, but we add this into acidic soil. So, Emily, what do you think is the impact when the acidic soil water react with the sodium carbonate? What will happen to the pH of the soil water?
It'll be neutralized.
Then why is it bad in this case? It's
Because
best.
the crops grow well in slightly acidic soil.
Yeah. So in our attempt to reduce the hardness of the water, we actually make the soil water unfavorable for the plants. Because by adding carbonate, you may neutralize it. So I'll say that this actually reduce the acidity of the soil water. Okay, which may make it unsuitable for the plant, for the crops to grow. All right, that's all. Okay, any questions for this hardness thing? Okay, this question deals with the cost of metals. And as you know, for the cost of metals, there are two very guiding principles. There's two guiding principles that will decide the cost of metals. Most of the time, number one is rarity. Number two is extraction methods. Extraction method, essentially anything that uses or anything that relates to electrolysis. By default, it will be more expensive. What do I mean by relate? So for example, right, let's say the extraction process actually make use of electrolysis. So by default, that will make the extraction process expensive. By saying relates, what I'm trying to put to the point is that you may for another metal which may not directly use electrolysis setup, but one of the materials to extract it. For example, this particular metal for extraction, it requires sodium metal. And sodium is needed, or rather sodium is extracted by electrolysis. So even though metal X doesn't undergo electrolysis, but its extraction process requires sodium, which is extracted from electrolysis, that itself will also make this metal more expensive because the raw material required to extract it is made up of an expensive material that is from electrolysis process. Okay, so that's why I put it as anything that uses electrolysis or has anything or any substance that's related to electrolysis will tend to drive the price of the metal up. But other than that, for rarity, I think it's straightforward. Okay. Now let's take a look at A. Gold more expensive than the rest. If you look at data, most likely is due to gold having very, very rare compared to the other metals. So compared to zinc, compared to aluminum, it is way more rare, so it should be way more expensive. Okay, so I'll mention something like this. Okay, something like this. All right, so let's look at point B. So question asked from the info, more abundant metal were discovered first. So definitely not. If you look at the most abundant is aluminum. It is only discovered 1,825 years from now. Whereas if you look at other materials, like even the iron is 4,000 years ago, and then the last three guys you have 5,000 to 8,000 years ago. So the most abundance. That means if we look at it, it doesn't really make sense. Things that is more abundant should be you can find it more easily. But instead, gold that is not so abundant, silver that's not so abundant compared to aluminum, they are discovered like at least 6,000, 7,000 to 10,000 years earlier than zinc. Oh, okay, actually not that much. 3,000 plus years earlier than zinc for silver, and about 6,000 years earlier for gold. So, Mariam, what do you think? Why do you think it works that way? I thought something that's more abundant should be more easily found, but instead gold was discovered way earlier. What could be this reason?
It was more abundant at where it was found.
I mean, gold, is it?
Yeah.
Actually, let's consider it is very constant in terms of the earth crust composition. So it is always about 8% aluminum and lots of 0.1 for gold. So let's keep the abundance consistent. Why would gold be more easily discovered? And why is it those three metals, copper, silver, gold, discovered way earlier than this? So which means can you look at the years of discovery against the metals? What does the years of discovery link to the way the metals are being found? Is there a consistent trend that you see here?
Is it the one with different color? It sound first.
Color, okay, the color may help. The one for gold, because gold, the colors is probably definitely a lot easier to spot. But if you talk about silver probably looks like a bit gray, as the same as the rest. Now let me give you another hint. Does this look like reactivity series? If you look at this as reactivity series, can you tie in based on your understanding of reactivity series against the date of discovery?
The less reactive the metal, the earlier the date of discovery.
Why would you say that? I mean, based on the chart, it is the more reactive the metal, you'll notice that they were discovered like only more recently. Like for example, against of the
Is it because the metals they are found by themselves, like they're not like found in compounds or something?
Something like that. You see, the last three guys are copper, silver, gold. We often say that they are not formally extracted because most of the time the last three metals are found to be in their organic state, meaning they are found as metals. So when you see a piece of gold on the ground, you will know that is gold. So that's why these few metals, the copper, silver, gold, being highly unreactive, they tend to be found in as a natural state. So it is actually extracted, or rather it's being discovered more easily because they are in their natural form. Now the rest of them, they probably all look the same. They are all metal oxides. So they probably look the same, and it's very hard to distinguish them. And also you notice there's a big gap. Everyone else is about 1,000 odd years. And then the rest is like 5,000. So it's also probably due to technological advances, right, within the last 2,000 years that allows us to actually extract the metal and discover that actually this metal oxide and this metal oxide are not the same. Because prior to that, if you want to do, for example, 4,000, you say 4,000 years ago, right? Iron, you can actually they actually extract iron successfully, right? But the other metals, you notice that they are not really extracted yet. Maybe because at that point of time, in fact, those new metals that's extracted more recently are most of them the electrolysis metals. So prior to the technology that allow you to extract them, so they are probably just regarded as a metal ore. As of like 4,000 years from ago, you can extract iron, but you can't extract the rest. So being unable to extract due to technological advances, they are not discovered until more recent years. Before that can be done. Okay, so generally, those that are discovered really, really early, by concept is always the more unreactive metals because they are already in their organic state. Okay, then as technological advances move, you will see that the iron, for example, is more easily extracted than the rest because it's lower in the series, right? So their compounds are more easily extracted. So you start to discover the less reactive metal first. Then as electrolysis, all this comes in, the harder to extracted ones, previously thought to be, I can't extract them, becomes able to extract already. That's why you see for potassium, calcium, all this, their years of discovery quite close to each other. So probably then they discover electrolysis and they start to use electrolysis to break down them. All these are different ores. And they start to realize that we can actually get different metals from all these different ores. That's why relatively this might coincide with the discovery of electrolysis that allows those metals in the upper block to be found relatively close to each other. Okay, so this is the one of the skills that you all need to infuse in reactivity at date of discovery. Okay, without no issue, let's go to the question proper. A more abundance one extracted first, answer is no, because based on the table, right, aluminum is the most abundant. And it is so compared to, so aluminum is a 1825 compared to, let's say, copper, right? So it's about 3,000 years. Then I will choose the case of the most extreme one, which is gold. I'll say being the rarest metal in the list. It was actually discovered first. Again, for this part here, we don't have to explain what we have mentioned just now. It's just using the data to show this fact. So that's all I will write for part B. So sodium, when is sodium found? There's a very precise year that we can target. Frederick, which year do you think sodium is discovered? Look at the table, give me a number. It can be quite specific. And for good reasons. Yeah, we choose 1807. Okay, 1807 is fine. 1808 is fine. Because you can see calcium and potassium is about 1807, 1808. So it should be later than calcium possibly, but earlier than potassium. So in the range that they are all about the same reactivity. So for this question, we can accept 1870 or 1808. Right, so let's look at part D, relationship between reactivity. This is the one that we mentioned just now. Okay, so I'll just put in words. Generally, more reactive metals are discovered later. So I need to explain. So this is the trend that we observe. So for the explain portion, I'll talk about the technology thing. Something like this. So I talk about the technology required to extract the more reactive metals. And for the less reactive ones, they are discovered more easily due to their existence as a metal most of the time. Okay, part E kind of question is the kind of question that is the kind of question that I will not ponder too much. In the exam, if you are stuck with this, I'll just move on. Notice our trend says the more reactive the metal, the harder is it to extract. So if it's harder to extract, that means it must actually have take a longer time to discover. But we know aluminum is not as reactive as potassium. Yet, right, if you look at the table, aluminum is a bit like probably about 17 years, 18 years later than potassium. So why is the extraction of aluminum not possible until later time, even though potassium and gangue has already been extracted by electrolysis? Let's look at, okay, if you visualize the compound, right, the formula, let's assume they are all oxides, okay? We are extracting potassium oxide, calcium oxide, and
Protective layer or something.
not the protective layer. It's due to the formula. Look at the formula of potassium, calcium, and aluminum oxides. What makes it so difficult for aluminum to be extracted when the other two guys, which are more reactive, has already been extracted already? Look at the formula. Can you all tell me something that makes it difficult?
The Al 3 plus, then K is just plus, and Ca is 2 plus.
Okay, so that is correct. The direction is correct. So what does the charge of Al3 plus make
Stronger
it hard?
electrostatic forces of attraction.
Therefore,
A higher amount of energy is needed to overcome the bonds,
why do you want to overcome the bonds?
so that you can get aluminium.
Because when you do it, when you do the stronger electrostatic thing, right, you're actually melting it, right? When you melt it, it's only forming aluminum oxide molten. You haven't extracted it. You haven't extracted it. But the direction is totally correct. If we look at part E, the reason why aluminum is so difficult to extract is because the electrostatic forces of attraction, right, between the aluminum 3 plus and oxide 2 minus is way stronger than the calcium oxide or the potassium oxide. Is way, way, way stronger than this, which makes, right, aluminum, right, at that point of time, 1,800 years ago, right, make aluminum extremely, extremely rare. Now, rare not the sense that there is very little aluminum in the earth crust. There is a lot of aluminum ore, but the pure aluminum is extremely, extremely rare because of this. So now the problem is, this actually makes aluminum oxide, right, having a melting point that is way higher. That means to extract this guy, right, you need massive amount of energy. Because remember, when we want to do this, right, they are all actually extracted by the electrolysis of their molten oxide. Now, this is the killer word, molten. And this is the single reason why it is so expensive to do electrolysis. Not only you need to run electricity, you need to keep your electrolyte molten. And the only way to keep the electrolyte molten is to heat it. That means you're constantly melting ores. You're melting the ore and at the same time using electricity. That's why it is very expensive to do electrolysis. And it's even worse, right, if your ore has a massive melting point like aluminum. So at one point, right, aluminum was, the price of aluminum is really, really very, very high, because to break this down, it actually requires you to make, to use a lot of energy to break it down into a liquid state before you can even do electrolysis. So it actually, at one point, this aluminum metal is seen as the most precious metal in the world in terms of cost. And in those medieval times, it is used in all the castles and all by the kings and the royalty and all. It seems to be a royalty metal until something happened. And then they totally screw up everybody. So those who invested in aluminum then thinking that it's a very precious metal, 1,825 years ago, something happened. What do you think was done that makes aluminum become trash? And then the price totally plundered. Remember, the cost of extraction is the most important thing to determine the price. So suddenly at 1,800 years ago, 1825 years ago, the price of aluminum plundered because somebody did something to the electrolysis setup. What do you think was done that makes it so cheap at the end of the day? Something was done to do something to the electrolysis process. Can you all think about what is it?
Give hint.
Remember we said that for electrolysis is super expensive because you need to do two things. You need to supply electricity. Number you need to number one, you need to supply electricity to do all the preferential discharge crap, the theory thing. Number two, you need to burn fuel, right, to melt it. Burn fuel to melt it. So the combination of these two costs will determine how much is it to extract the metal. And previously I mentioned that aluminum has very high melting point. So the cost of keeping aluminum oxide molten is the killer point at that point of time. And that makes the production of aluminum extremely rare. And that's why it's used for royalty. But after a while, someone discover that I can do something. Then it makes the whole process a lot cheaper. So I think you have to think about it. What did the person did? Did he, because there's only two things that make the electricity expensive. It's either the electricity part or keeping it the molten part. So he made an improvement to one of these two processes, either the electricity process or the melting process. What do you think he might have done so that it is a lot easier for it to carry out this process, which make aluminum a trashy metal, so trashy that we use it to coat our aluminum foil? What do you think? Remember, it's all about cost. In which area can we save on? 30 seconds, y'all get it, get it. Don't get it, y'all won't get it. Another hint, it's not electricity. They make some improvement to the melting boiling point. It's not because they suddenly discovered nuclear and then using nuclear energy cheaper. No. Electrolysis are not due to electricity. It's due to
They isn't that they added some like other substances
to do what?
to, like, for example, like to decrease the boiling point or something.
Melting point. Melting
Yeah,
point.
melting point.
Yes.
Like impurities, is it?
It is the impurity concept.
Yeah.
So the improvement here is an impurity was added to decrease the melting point of Al2O3. This is under Sec 3 topic when you all do the effects of impurity. The impurity will lower melting boiling point. So the pure aluminum oxide goes for like maybe 2K plus degrees Celsius. But when you add this impurity is called cryolite. Cryolite is a compound of aluminum. Okay, and this is added to molten aluminum oxide, right? To lower its melting point to about 600 plus degrees Celsius. So the melting point easily reduced by 3 times. So the amount of energy that you need to keep it molten becomes drastically cheaper. So it becomes very, very cheap for the aluminum to be extracted prior to the discovery of this guy. So overnight, the price of aluminum plundered because now it is so much cheaper to harvest your aluminum from the ore. Now, which makes aluminum so-called not precious metal anymore. Okay, so let me put this in here. So this one is basically, you may not have done this. It's more of understanding the electrolysis setup, right, for molten. You need to keep it molten. So if you can use less energy to keep it molten, you save a lot of costs. So prior to the discovery of this, right, they have difficulty melting aluminum oxide. That's why it is discovered later, because without the discovery of cryolite, it is not possible to melt aluminum oxide easily. Okay, so this is what I write. The name is called cryolite. Yeah, it is so high that in the first place, you need to have a furnace, right? To be able to store this aluminum. Because its melting point is 2000 plus. So if your melting point of your furnace and all is not higher than that, the whole furnace will melt with your aluminum oxide. So you have to do changes to it. So the change here is to add an impurity using the concept of impurity lower melting volume point. Sorry, lower melting point. And for theory's sake, do remember, impurity will increase boiling point. It will decrease melting point. Please jot down whatever you need for this. Those who are done, you can proceed to the next part. Marie, for anything that's aqueous, right, in the state symbol, anything that's soluble, the state symbol, we will put AQ, agree, right?
Yeah.
Sodium oxide soluble.
Yes.
Sodium all soluble, right? Okay.
Yeah.
So sodium oxide. Do I put it as AQ? Feels weird, right?
Yeah.
What's the weird part about this?
It's not like in a liquid form.
Oh, it's not it's aqueous. Sodium oxide aqueous, that means it's sodium oxide in water, correct?
Yeah.
What happens when sodium oxide goes into water? Is there any meaningful things that's formed here? It forms one product. Look at all the ions, or look at all the what do you call it, elements there. What do you think you form?
Sodium hydroxide.
Sodium hydroxide. Okay, so why I bring this up? Because although we always mention that soluble substances we put AQ, oxide of soluble metal oxides, we put AQ is a bit weird. Because the moment they touch water, if they are soluble, they will form the hydroxide version of it, right? It will turn into an alkali. So for metal oxides, right, I would highly recommend you to avoid this. Instead, for metal oxides, state symbol, just go solid. You might say that I cannot put solid because sodium oxide is soluble. Yes, but this solid, when dissolved, because for other things it's quite different. It's not the same narrative as sodium chloride solid. I put into water, what do I get? I get sodium chloride, AQ. That makes perfect sense. But when sodium oxide solid, you put it into water, it does not form an oxide that is aqueous. Instead, it turns into sodium hydroxide. This is the correct version when you put it into water. So for soluble metal oxide, got this thing that you might want to look out for when you do ionic equation. Okay, so be mindful of this. Okay, ionic equation for the calcium oxide with seawater. So this is the same thing. Calcium oxide soluble, you will form calcium hydroxide. So technically speaking, right, I cannot have calcium oxide. It is soluble, but I do not put it as AQ because after dissolving into water, by right, this is what it should form. You will form your lime water or calcium hydroxide, AQ. Okay, this is the chemical equation. Okay, the chemical equation is the same as the chemical equation for sodium hydroxide formation. It's the same thing. But what about ionic equation? In the spirit of things, ionic equation, anything that's aqueous, will split them up into their ions. But you look at the left-hand side, right? There's nothing for you to cancel. So quite awkward, the ionic equation will look like this. The calcium oxide is staying. The water, it stays. But the calcium hydroxide splits into calcium 2 plus AQ and 2 hydroxide. Minus AQ. There is no cancelling of any ions because on the left hand side, there's no free moving ions for you to cancel. There are no spectator ions here. Because previously there are no free moving ions in the reactant side. On the left hand side, there's no free moving ions. So the only free moving ions you obtain is from the ionization of the alkali. Okay, so that's all for our part A. So do know the difference between weird questions like this, chemical and ionic equation. They look strangely close. And of course, the metal oxide thing. Okay, part B, the question says the precipitate. So if, this is basically extracting elements from the sea. So the question here says it's cheaper to mine magnesium from the sea water as compared to the Earth's crust. So Earth's crust, you know, magnesium is electrolysis and all these, right? So it's going to be expensive. So instead over here, we do precipitation process. We precipitate out the magnesium from the sea, and then we pull it out from there. Okay, so question here mentioned is more easily precipitate than calcium hydroxide. If something can precipitate out easily, most likely is because the compound itself is pretty insoluble. Okay, so the only reason why I'll pick this will be it's actually less soluble in water. Compared to your calcium hydroxide, so hence it will actually form PBT more easily. Okay, something like this. Okay, part C. So we're using neutralization to obtain the magnesium chloride. So how the solid can be obtained? This is a solution that is AQ. So this is under separation technique in lower set, not lower set, in early set 3. So you can actually use this is actually salt preparation for a soluble salt here. So now it's in a solution. How do you take it out? So in this case, in the magnesium chloride, you can actually do the crystallization, discrete crystallization, evaporate the magnesium chloride solution to form a saturated solution. And then mention allow solution to cool. So these crystals will form. After that, we'll filter the crystals. Okay, next we'll do the washing and drying. So if you want to do washing and drying, because this is a soluble salt, okay, you need to be able to wash the crystals. Okay, we'll wash it with small amounts of cold distilled water. Okay, why do we want to go through such a issue? Because it is a soluble salt. Magnesium chloride is soluble. So if you want to clean the salt, if you want to wash the salt, you cannot wash it with large amount of water because it will lead to the salts dissolving. Number two, you cannot use warm water because when the temperature is high, it tends to have better solubility. So to keep your salt intact, okay, every time you do washing of soluble salts, always use this term. But when you do precipitation, okay, insoluble salts, and you use the same term, you cut and paste this template, and you write, wash the insoluble salt with small amount of cold distilled water, you will be penalized. Because that would suggest that you do not know the fundamental reason why we are washing the salt with small amount of cold distilled water. Okay, it is a step that is only reserved for soluble salts. Okay, please remember that. For insoluble salt, we will just say, wash the salt with distilled water. You don't have to say large amount, you don't have to say normal temperature or whatever, doesn't matter. For insoluble salts, just mention wash with distilled water, but for soluble, please write this. Okay, after washing, the standard step will be press dry between filter paper. This is standard. Okay, DF is a bit of redox, is a bit of redox and a bit of equation writing for what do you call that, electrolysis. And a bit of redox here also. So can I give you a few minutes to look at this, especially if you haven't done this yet? Okay, you haven't done this yet. Y'all take a look at this one. Time now is 3:23. Can I give you a few minutes? Let's say, I don't know, 5 minutes, 3:28 p.m. Take a look at DF carefully, and then we look at it. Reduce melting point of aluminum oxide by adding an impurity. So this case here, we suggest that extraction of magnesium, some sodium chloride, calcium chloride, blah, blah, is added and all. Okay, so question says why zinc cannot be added. Okay, so you should have seen the reactivity of the metals used. If you were to use zinc, zinc is actually lower than magnesium. So if that's the case, then zinc will have undergone preferential discharge compared to magnesium. That doesn't work anymore. Whereas the other two impurities that was added, sodium chloride, calcium chloride. Okay, some may wonder if I add all these different ions, because just now for the cryolite, it was like compound of aluminum. Whoops. Compound of aluminum. So it's aluminum added to aluminum. That looks fine, it doesn't contaminate. So one of the common wrong answer is that sodium, it may contaminate it. No, not really. Sodium and calcium doesn't contaminate because they are still lower than magnesium, higher than magnesium. So magnesium is going to undergo PD. So the only reason for this is because zinc is actually lower. So zinc will undergo PD instead of magnesium. So we can't collect magnesium from there. So this is what I will write. Okay, next. Half equation. So for the magnesium chloride, the chloride will go off on the anode side. Cathode side is always the metal. Okay, next. Okay, so it's apparent that there is a reduction here. My answer is no, because chlorine is reduced. Okay, I'll use the standard template, right? Okay, because the oxidation state, chlorine actually decreases from 0 in the chlorine to -1 in HCl. So there is actually a reduction. Hence, we say that reduction is also present. This is the easy one. Now, can I ask you, anyone knows how to explain the oxidation? The reduction is easy. How to explain oxidation? So let me put a question here.
Cause it's +1, right?
Who is +1?
Cl.
Over here, correct?
Yeah.
It's due to this weird compound. Whenever you see this kind of weird compound, right? We have to calculate chlorine. So this is actually +1. This is actually -2. This is actually +1. So chlorine instead. So in this kind of formula, right? You need to remember that chlorine is not +1. Oh, sorry, it's not -1. Okay, as norm, it is actually +1. Because if we were to assign chlorine to be -1, right? This is +1, this is -2, this is -1. Then the overall oxidation state here will be -2. Okay, it is a compound, it's not an ion. So if it's not an ion, it cannot have a charge. So as a compound, someone has to sacrifice it. And the one that was sacrificed is chlorine. I must ask,
So is this a disproportionation reaction?
yes, yeah, coming to disproportionation. Yeah, so in this case, right, I will say that chlorine in this case is oxidized. Okay, because the oxidation state of chlorine in this case is increases from 0 in chlorine to +1 in HOCl. Now, in this case, I will also mention that chlorine undergo a special kind of redox, which is undergo disproportionation reaction. Wrong spelling, I think. Okay, let's try again. Disproportionation. Okay, let me Google. Like somehow this thing slipped my mind, damn it. Well, it's actually correct. Okay, it's actually correct. So disproportionation reaction. What is a disproportionation reaction? That means it's the same item, aka the chlorine in this case, it undergo both oxidation and reduction. It also means that this same item here is oxidized, meaning it's a reducing agent, and he is reduced, meaning he's also the oxidizing agent. But more importantly, disproportionation reaction is a reaction where the same thing, the same item, undergoes both oxidation and reduction. Okay, that's all. Yeah, this one is a good point to stop. You all jot down everything you need. Any questions, let me know. If no